Okay. So this week I'm not going to do Arduino stuff. I had planned on doing some stuff with LCDs. There's a LCD shield out there that's kind of neat. It's got like 5 buttons. Each one has its own resistor and it ties into one of the analog to digital converter channels. So depending on which ones or combinations of which ones you choose, you'll get different voltages at the ADC, and you can say all 5 of those buttons are fed into one input and you know which button was pushed. I did some research because I wasn't sure absolutely that it would work with the Ethernet shield, but I thought it'd be really neat to put it on an Ethernet shield, bring it in and do some of the exact same stuff we did last time, only have it throw little words and whatever up. And then I figured out that it won't fit on top of my Ethernet shield because the PoE things, yeah, that's it right there. Share with the class. The PoE thing's too tall, and it might be able to work with it, but the legs on the pins are too short to be able to go all the way down and make any contact. And so then I'm digging around and looking to see, well, do I have any just empty
like extenders,
yeah. And I couldn't find any. And then I was on vacation last week, and you know, I didn't get anything done.
I have some in my car.
I'll tell if you got them, I'll take
Okay.
them off of you later, and maybe I'll go play with it here, not tonight, but some other night. So there's been some questions from different people, you know, going back to some of the basics, wanting to see some of the behind the curtain stuff. So I thought tonight we'll go back behind the curtain again and go back to some of the basic stuff we talked about before. And I think what I've got drawn up here on the board behind me is easily an hour's worth, depending on how long-winded I get. Or because I've already drawn it on the board, maybe it's a half hour's worth because I won't actually have to draw it while I'm thinking. You know how that works. So we'll talk about resistors, inductors, and capacitors. They are our 3 basic passive components, which means they don't amplify, there's no inputs, just voltage goes on, two-port device. It has voltage in, voltage out, current in, current out. So we'll go back and look at the how and why on some of them. And I won't go real deep in the math, but I'll give you a little bit of the math and some of the things that you do that use those types of things. So we'll start with a resistor. So we've talked about before, this is the symbol of a resistor. Resistance is in ohms. So what is a resistor? I'm still going to draw on the board some. I'll draw in a different color though, probably. So a resistor is a piece of material. So we talk about wires, and I say that wires have no resistance, and then I tell you that's a lie, but for simplicity, they have no resistance. So what you have in here is this hunk of metal. Let's say this is a piece of copper for now. It has all these little, I'm sorry, I'm going to use the Bohr model for an atom, which everybody says isn't true anymore, but it's easy to draw. So you've got all these little atoms, right, with electron clouds going around them and so on and so forth. Right? Got atoms. What makes a conductor is it has a hole right there. Or actually, I'm sorry, a conductor's the opposite. A conductor has a lot of these things when they want to bend together. Copper, for instance, is a positive or is a negative ion. It has an extra site. If you go back to the atom, you got your nucleus, and then you've got orbit 1 can have 2 electrons in it. Orbit 2 can have 4 electrons, I think. I probably got this wrong. Orbit 3 can have another so many and whatever. And there's actually spins on this. So you've got one S1 and one S2 is upspin and downspin. 4s1, 4s2, 4s3, 4s4, and then there's like a 4p, and it goes
Yeah,
on.
the P's and D's and F's and yeah.
Yeah, and every good boy does fine, and it plays music and all sorts of neat stuff.
I hated that part of
So-
chemistry.
In the case of a conductor, there's two ways you can conduct. You can come out here and you can be one short, and you have a hole, and so you want to take an electron from somebody else. So if you've got a hydrogen atom, for instance, it's got an electron. I'm sorry, this is an electron, and it's got a hole. And then over here we'll have a hole and an electron. And then you stick an oxygen in the middle. And his last whatever ring has two holes, has two extra electrons. So he's got a setup that looks like, maybe I've got it backwards. This works either way, and that's why it's easy to get it mixed up. So in the very outside ring of the oxygen, here's the part I can't remember, there's either only two electrons, bang. One electron goes to that one electron goes to that one. This guy's sharing an electron with him, he's sharing an electron with him. Everybody's happy, you're at a charge equilibrium, right? Now we're going to stay together and we've got water. Or it could be the other way around, maybe this one's completely full and there's two holes. And what's really happening is the hydrogen's one electron is doing this. But I honestly think it's this way. And the reason I think that is because if it wasn't that way, sulfuric acid wouldn't work the way sulfuric acid does. Water is what's called a polar molecule, a bipolar molecule. So the oxygen sits here, and the two hydrogens sit here, and here there's a heavy negative charge, and here's a positive, because those extra two electrons are over here. And so your water molecule acts as an ion. Things that are negatively charged want to come to this side, and things that are positively charged want to come to that side. And it actually, sulfuric acid is H2SO4, hydrogen gas, and hydrogen sulfate.
I always get the fates and fides.
Yeah, and then there's like an oxalate. So what happens is this actually rips the H2 and the SO4 apart, and now you've got hydrogen molecules in solution, an H2, and an SO4, which is an ion in solution, and it's a negative ion, I think, floating in the solution. Maybe it's a positive ion, but anyway, now they're floating in solution, and what that lets an ion travel from plate to plate and move charge, transport. And when you charge it, you're pushing that ion back over to the other plate, where it sits there because there's a difference in charge inside. So now, with this badly drawn and poor understanding of what's going on here,
Is there a race up there for you?
there it is. I don't know where it is though.
Right up
I saw it a minute ago. Oh, and there's other colors too. I don't have to stick
Yeah.
with just these three.
Yeah, I bought a whole pack
I was
for you.
really wanting green and purple earlier, but
Yeah, there's green and purple and blue.
and brown and blue. All right. Well. All right. So now we got all these atoms, and God, I wish I could remember if copper. Copper's got to be a positive ion, which means it's got holes. So I'll put little holes out here. And the reason I think copper's a positive ion is because when you grow logicking my way through this, which is probably wrong, when you have dendritic growth, it grows from the negative to the positive, but it's actually because the the ion is moving from the positive one down to the negative one, and then it's growing back towards the other. And we'll get into that in a minute. Maybe. So what happens is your electron comes moving in, right? But he can't go anywhere except where there's a hole. So he goes here. Well, now another electron comes in, and he's got nowhere to go, but there's all these, right here at this end, there's all of these atoms that have an electron that normally don't have an electron. So it's really easy to push that electron over here, and that one goes in. And it's a daisy chain, right? One comes in and one goes out, so now he bounces down there, and then maybe he bounces over there, and then over here, and then over there, and out that way. And they're really going every which way inside this wire. But in general, the average movement is that way, and that's your current. Now when they're jumping back and forth this way, all over the way, back and forth, they're converting this momentum energy into thermal energy. That's heat. And this having to bounce around down at the very basic physical level, that's what resistance is. Your electron can't just go running through. He's got a ping pong ball around and bounce off of things. Sometimes they'll even bounce backwards.
So a lot of resistors have carbon, so carbon has more holes than copper, I guess. So it's more.
So it works either way. So you can have one that's got the one extra electron out there, and you push it in, and then you start talking about. It gets really esoteric, right? And it's been a long time since I've delved into the math. I mean, it's been 20 some odd years since I've delved into the math. You start talking about hole flow vice electron flow.
Okay.
The effect is the same. You've got extra holes, and you put an electron in. You can look at this and say, oh, well, this is an electron going this way, or this is a hole going that way, right? The number of holes and the number of electrons always balances out. So the equations are all identical. You just have to choose the notation that you're going to use, and don't change. If you flip in the middle, you'll break everything. But as long as you stay within the same notation and the same theorems the whole way, all of these equations everywhere in the world will be exactly the same. It's just that as long as we're talking about these, now when we get into semiconductors, diodes, transistors, things like that, now it matters. Because now you're playing with excess holes and excess electrons in the same piece of material, in two different pieces of materials that are abutting. And it causes very interesting and neat things happen that allow the electronic age. So, I can think my way through these and tell you, but, you get down to that atomic level and I can't remember. But, so, we call this some amount of resistivity, rho, Greek letter rho, and resistivity is in ohm meters. So what you have here, if this is a wire, it is a circle that's extruded out really long, right? And so it has an area here. In the case of a circle, it's pi r squared, right? So if I take purple, if I say A, I'm going to do R, I thought I had it written down somewhere. R resistance is equal to rho times the length L divided by the area A. Length is in meters, area is in meters squared, because R is in meters. So meters squared, this is meters, this is ohm meters times meters, I should put that up here. Ohm meters times meters is equal to ohms meters squared over meters squared equals ohms. So, for a given material, a wire, a bus bar, a piece of copper, silver, whatever your conductor is, laying somewhere in the direction the current's flowing, the cross-sectional area times the length times rho. Actually, I'm sorry. The cross-sectional, its rho times its length divided by its cross-sectional area is its resistance. So if I have a copper wire that's this big around and this long, it's not 1 ohm, it's really, really small. But now if I've got 2 of them, now it's 2 ohms. Now it's 3 ohms. Now it's 4 ohms. The longer it is, the more resistance it is. So this is what we talked about in the first couple classes about, is it 110, 120, and 115, what's the voltage at the wall? You're guaranteed when it comes in the wall at full load to be 120. If the wiring's done correctly on the longest run for that gauge of wire for the current that the breaker's set for, it'll never go below 110. And that's going back to voltage is equal to current times resistance. But resistance is equal, a function of that is the length of the wire. So you can back that out and you say, well, if this is guaranteed to be at least 110, and that's guaranteed to be at least 120, that's a 10 volt voltage drop between the two, 120, 110, and if it's a 15 amp circuit, then that's V equals IR equals V is 10 volts, 120 minus 110, right? 10 volts equals 15 R, or R equals 1.5 V over R. Go backwards. 10 over I over horseshit. V over I. I'm sorry, yeah, I had it right the first time. V over I equals 10 volts over 15 amps. Whatever that is. 1 over 1.5, which is a little bit around a half an ohm somewhere. And then you can say, oh, but that wire's whatever the maximum length is that you have, 60 feet, 100 feet, and that tells you the resistance of that particular copper wire per foot. And in fact, when you go through and look at the tables and you start talking about different gauges of wire, it says this is the ohms per foot. And so you do all your calculations when you're doing somebody's house or whatever you're wiring to take into account what your maximum allowable voltage drop for the given current is, and that gauges your wire for you. Then there's other things about factors of safety and how much heat that's going to give off in your wall and some other stuff. And they really don't care how hot it gets in your wall.
Yeah, you mentioned what you're allowed to have in there. I was shocked.
Well, it's based on the insulator that's on it. So, yeah, you don't want it to get 600 degrees because you're going to burn the wood and it's going to start on fire. But the electric code says, well, we want to keep it below that. And then but long before the wood and stuff catches on fire, the insulator's going to melt and or burn. It's going to melt, and then the two wires close to each other are going to arc, or it's going to catch on fire itself and go. And so the maximum allowable temperature is based on the kind of insulation that it's in. The kind of insulation you use is depend on where it's going to be. If I'm on a ship, they have what's called IEEE Class P wiring, which means I can throw salt water on it, it can be sitting in the sun, I can throw oil and hydraulic fluid and diesel fuel all over it, and it'll be happy with it. But it's not allowed to get above, I think with all the safety factors, they want to keep it below 95 C, which means it's this shy of boiling. And when I've done designs for this, I say, screw that, I don't want something if I touch it, it's going to melt my skin off. I'm going to put a few more factors of safety on that, or actually what I'll do is I'll go down and I'll use, it's not allowed to get hotter than 60 C. Because 75 C, loosely, is the point where you go, ow! But it doesn't burn you. Right? You know, if you grab hold of it and hang on to it, it's going to burn you. But if you, yeah. So I try and keep it down in the 60 C range, and we go from there. Which I find that when I go out and I size everything for the way I like it, and then I go and I pull some manufacturer's whatever big honkin' 480 three-phase lineup, my connector holes are too big because they're using the smallest wire they can because they're cheap bastards, and they're expecting that, well, you're not going to be running this full bore all the time out on a hot deck and whatever else, and it's not going to get so hot it's going to burn you. Yeah, they're probably right.
Sometimes.
Usually. So this has an interesting effect. So we've got length here and height times width. And you think, well, that's kind of weird. You don't see square wires very often. But if you go on to a semiconductor, when I do my layout, and this is true for everything, now we get into this weirdness where if I look straight down on this, if I look straight down on this, and if my L is equal to my W, I have a square. And then I have some height here, and I'll assume current is going this way. So now I see that length and width are the same, and I end up with this weird thing where rho in ohm meters is equal to R times L in meters over width in meters times height in meters. But these are always the same, so they're 1. And now my resistance is rho over H, exactly, because it's a square. And I find this amusing when I listen to these guys talk about siding and shingles on houses these days, because they talk about $500 a square. Well, for them a square is 10 foot by 10 foot, I think. When you're in semiconductors and you're laying out tracks, you think of everything in squares. When I lay down a line like this, just a piece of material, whatever it is, it's only like a couple of microns thick, I look at that as a bunch of squares. And when I look up my process to say whatever foundry I'm going to go to, they will tell you for this particular material that you use, it's this many ohms per square. And now I can say if that's 1 ohm per square, or X, 1, 2, 3, 4, 5, 6, 7, 8, that's 8X ohms for that length. If it goes around a corner, there's a little bit of weirdness where you go around the corner, but it's close enough. So you can actually just count all the squares and say, I know this is going to be this many ohms. Plus or minus some ambiguity.
When you say tracks, are you talking like PC traces, or are you talking...
That actually works too.
It works too, or are you talking actually silicon?
I'm talking down on silicon as a way
Okay.
they do. The foundry comes back to you and says this many ohms per square. Because you're using funky materials. Some of it's silicon dioxide, some of it's aluminum, some of it's tungsten, some of it's copper. When you go on to a circuit board, the standard circuit board is 1 ounce copper. And if you look at what that is, it will, 1 ounce means it's 1 ounce per square foot.
Okay.
Which means it's,
Yeah, paper thin.
it's like 2 mils, 2/1000 of an inch thick, I think. But if you want to, you can look at that as ohms per square. You know, you got to go back and look it up. Look. If you can find it in a table, you got the internet there. You can probably find it. You can just look up ohms per square for 1 ounce copper, and from there it'll tell you. But there's other things because copper has like a thermal coefficient. It changes its TCR, thermal coefficient of resistance, changes a little bit. But
Yeah, what do you know? It's talking about all the same.
yeah, see, there you go.
Yeah.
I didn't even look it up beforehand. I'm doing this all from memory.
The equations look dangerously similar.
Yeah, they are similar. I did look up rho today because I couldn't remember the exact units, and that wasn't making sense to me. But so now, if I've got a material that as it heats up, it expands, and those atoms move further apart, then it's more resistance for them to go through, and I've got a thermistor, a temperature-sensitive resistor, and I can use that to measure temperature. And what I do is I choose a material that's especially sensitive to temperature, so it generally has a high expansion.
So you're measuring the change in resistance through the material based on temperature.
Yes, and they calibrate them. You can, if you look at the common ones are like a PT100 and a PT1000. The PT, if I remember right, there's two different. It might be positive temperature coefficient. So as temperature goes up, the resistance goes up. There's some materials that have a negative coefficient. So as temperature goes up, the resistance goes down. I think it's also. I think platinum is a positive temperature coefficient. And so a lot of those PTs that are precisions are also made out of platinum, and that's part of why they're so damn expensive. So I'm not sure if PT means positive coefficient, positive temperature, or if PT means platinum. But a PT100 is, if I remember right, it's 100 ohms. A PT1000 is 1,000 ohms.
Okay.
And the numbers actually mean something on them. They're not just like the version
They're
of
not part numbers.
No. And you can get them calibrated. I've got... The truth is it's a curve, and the resistance looks kind of like that, or maybe it's that way as it gets hotter. It looks like that, and they try to, depending on the material, they try to choose like 2 points here as your operating range, but if you look at that, there's still a little bit of a dip in it. And so there's a formula that'll estimate this, and they give you the ends, and they give you a K factor. Is it K factor? It's some sort of a factor that goes here. But if you get a more finely tuned one, they can give you up to 5 usually in there, so that you can do a piecewise linear because you want a really good curve, and you're really worried about how good stuff is. So. And I've even gotten them back where they had 100 different temperatures on it, on half-degree C things. This is the resistance, this is the resistance, this is the resistance. They take each one, they measure it, it's got a NIST caliper. It has a National Institute of Standards traceable temperature source and measurement device that they used to tell you what it is. And so you have it exactly right there, and you can put it in as a lookup table if you want. Fun stuff. Mostly useless, but interesting in some cases. Now, used to be, original resistors were carbon resistor. They would, I'm going to make this up, but they would take wood and they would burn it into charcoal, and they would crush it all up into a dust, and they would put some binder in it, like some Elmer's glue, and they would squish it together as hard as they could, and it made this slug of carbon. And they had real problems. The biggest problem was where this slug of carbon attached to the wire here, coming out, right? Because they're different metals and they don't like to be glued together, and they would fall apart. And there's actually a couple of really interesting articles if you go back. They're really nerdy articles that are interesting to nerds if you want to go back and read about some of the development of resistors back in the 40s, 50s, 60s, and the pains they went through. And so you used to be able... So I mentioned this before, you will never, ever, ever... You used to be able to buy... Resistors were so hard to make that you could buy cheap ones that were 20% tolerance, and then 15% tolerance, and 10% tolerance, and 5, and 2, and 1, and well, you didn't even use 1 was like, and you paid more and more and more from them. And you'd be thinking, I'm a smart dude. I'm going to go buy 15% resistors because it's a Gaussian distribution that's, what is it, 3 sigma is 99%, right? Well, it's 6 sigma, but it's 3 sigma either side is 6 sigma, and that's 99 and a half, I think, or 99, I don't know.
Yes.
99%. So, and this is unity, and so from here to here is 99% of all your stuff. Everything else is these loose outliers, and you know that most of them are going to fall there unless there's something in the process that's skewing it one way or another. And you'd say, I'm a smart dude. I'm not paying $23 for a 1 ohm resistor. I'm going to spend $2 on a 1 ohm resistor that's 15% instead of. And what you would find out is you come out however far 15% is, and it would look like this. And those really expensive 1 ohm resistors all fell right here. And those not quite so expensive 2 to 1%, and the 2% kind of fell right here. They were binning them. And so if you said, I'm going to be clever and I'm going to go buy 15% resistors, you were guaranteed that you would never be closer than 15% to what you really wanted to be at. Now today, we don't make them out of carbon. You can buy what's called a carbon film, where I'm not exactly sure how they make that, but it's a plate like this, and they implant the carbon on it, and it can't move, and it can't fall apart, and it's like a piece of metal here and a piece of metal there, and it's ceramic, and it's laying on it. These are actually some of the most satisfying ones to overload and cause them to overheat because they burn nicely. Now what you'll usually find is you'll find wire wound. And so what they'll come in with a wire, and the wire loops like that. And then they weld them. They use a spot welding technique to spot weld them on. And so now when you're looking at resistors, it's hard to find anything worse than a 5% resistor. And I've got even 0.1 and 0.01% resistors in reasonable sizes aren't horribly expensive. You buy them by the 1,000 and they're, 5 cents a piece. So, I mean, still, when you get down to 0.1, 0.01, 0.001, I've seen, yeah, they can be pricey, but it's not like a 1% was 20 years ago. So, and that's
Where you had to write a document in order to buy one?
well, it's good and bad, because you go out and you say, that you can buy something that's within 1%, and your circuit's going to work for most of the time. But what we've lost as a part of this, especially for young engineers, is the ability to go through and look at your circuit. Okay, this is what I designed, and then go through and understand where the sensitive points are, and what happens if this goes out to 5% and this goes to minus 5%, and basically mentally Monte Carloing a circuit to say, these are the spots I know from experience and what I've learned, that these are going to be the really sensitive spots, and what happens if those go out. Because it would be more expensive to make a circuit because you had to build in the tolerance. It had to work in all these cases. When temperature was way down here, temperature was way up there, and these things are moving around, and you're using plus or minus 15%, so it could be plus 15 going this way, but it could be plus 15 coming back that way. At the same time, this is doing that. And you had to make sure that your circuit was stable, and you knew that it was going to do what you wanted to do, and when you designed it, you set the minimum limits at the maximum temperature excursions, say, right? So I always know that this is going to do exactly this as long as you stay within these corners of the box. But you're building in a lot of extra overhead into the circuit. You're making it a little bit more expensive. You're spending more time doing it. Makes it a little bit more expensive. Now we've got more and more precise parts. You can go in and be more and more precise. Not worry about temperature ranges, but younger generations especially have forgotten all this. Because they never learned it, they didn't need to. And you see somebody get bit in the ass every now and then when, oh, it's at the 15%, let's stick this 10 ohm resistor in here. And, or you look at somebody's design that they've done and it has, you look at it and you say, why is this a 10.001 ohm resistor? Well, that's what it's got to be to work. Well, what happens if it's 10.0009, right? Oh, well, it goes crazy and doesn't work. You can't do that, you know. Now we got to go back and redo this because that ain't going to work. Well, it works here. Look, see, I simulated it. Here's a breadboard. Here's a pile of components. Go build it.
Build it. See what happens.
Tell me if it works. Because somewhere along the line, this copper trace that you didn't count in your equations has a spot that's a little bit narrower, like this.
Mm-hmm.
And now you model that as this resistor, and that resistor, and this resistor, which is a higher resistance than those ones. Or it's thinner, or whatever.
And there's your 0.00.
And there's your 5 zeros. Yeah. Now, other practical things, you don't see this anymore that I'm aware of. Old telephones. You talk in them, they worked by doing this. They had a case, and if you think about, especially an older speaker where it's got the paper cone, and then like a mylar or metal disc in the middle. So this would be the paper cone, this would be the metal disc, and this was actually relatively compressed carbon in there with a lead going in and a lead going out. And when you would speak, the sound waves would push and compress and decompress that carbon. And now you've got a signal coming through.
Wow.
And that's how the original microphones were made. And that's also why when you listen to, that's part of why they're so scratchy sounding when people are talking, because God, carbon is awful.
Yeah.
And when you start talking about really sensitive circuits, I did not look this up. You talk about noise in your, so I think I've said before that I'm an analog to digital guy. I've done a lot of this stuff up on the front end to turn the real world into bits. And the noise of resistors is just about the #1 noise source in your system. And the perfect resistor, let's see if I can get this right. The thermal voltage, because remember we talked about these things bouncing around. Well, now they get hot and they start bouncing more and bigger jumps and littler jumps and more side to sides and whatever else. The thermal voltage is Boltzmann's constant. Actually, that's K. Boltzmann's constant times temperature to the 4th square root. You're looking it up. Thermal noise is what you want to look. Resistor thermal noise is what you want to look up.
Thermal noise.
Just go to the images. There'll be somebody has an equation, or you got the equations right there. Right there, 4K T epsilon R. B, 4K T B to, there it is. Just 4K T B R. That's it right there. 4, Boltzmann's constant. This is T in kelvins. This is the bandwidth. And this is the resistance in ohms.
What's the bandwidth?
So, if I'm doing voice on telephony, I want an 8 kilohertz bandwidth. That's gonna,
it's okay.
that's gonna So I'm gonna filter off here because I don't care about that, and for you and me to talk 4 kilohertz frequency, Nyquist, I want to sample at 8, so 8 kilohertz bandwidth. So I'll set this up at 8 kilohertz. I won't digitize any faster than 8 kilohertz because I don't need it and it takes more data bandwidth. So my analog bandwidth then is 8,000, and if it's room temperature, that's 300, about 300 Kelvin. So now I've got 8,000 times 300. Boltzmann's constant is like times 10 to the negative 12. Or 10 to the negative 9th. You can look that up real quick too. I don't remember off the top of my head. It's small.
10 to the minus 23rd.
Oh, 10 to the minus 23rd. Is it 1 times 10 to the minus 23rd?
1.380.
Okay, 1.4 times 10 to the negative 23rd. And let's say I've got a 100 kilo ohm resistor. And I've got a number 4 out here. So this is 8 times 3 is 24. And that's a 1, so that stays the same. And so that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 4 times, that'd be 96. Times 1.4 would be 96 plus about a half, which would be 48. 9 and 4. Uh, 9 and 4 is 48. 8 and 6 is 14. Carry a 1. 9, 10, 144. And so 23, 22, 21, 20, 19, 18, 17, 16, 15, 14, 13, 12, 11. 1.44 times 10 to the negative 11th. But the square root of times 10 to the negative 11th is going to be times 10 to the negative 3, 4. That'd be about 1.44 is divided by 2 is 0.7. It's going to be about 0.2. 2 times 2 is 4. 9. 4 times 4 is 12. About 0.4 times 10 to the negative 3 times 3 is 9, negative 5. If I'm doing my Arduino, that's like 1 count at 10 bits on 5 volts. So that's in the noise that I can read in my digitizing circuit. I'm doing this all in my head, so I could be off by a 0 here or there, but resistors add noise. You try not to use resistors. If you can help it, don't use a resistor. There's other things you can do that work, have an equivalent function, but have less noise. That's not such a big deal on top of a circuit board with all sorts of tracks and layouts and everywhere. Your resistances are going to be small, but when you're doing really super stupid sensitive analog circuits, I've done stuff that's 16-bit type stuff and high speed, so it's got a wide bandwidth. Like, well, I mean, if you want to think about your Wi-Fi portal, that's 2.5 gigahertz with a 2. Is it 200? I think it's a 200. It's either 200 or 400 megahertz bandwidth. So now that 8,000 became 400 million, and now that million ohms only needs to be a little bit, and my signal strength is practically nothing. And you start talking about radios where, yeah, I've got a 50,000 watt antenna there, but we talked about it's a wavefront, right? And every meter it gets, it drops by the, it's like the radius cubed is the drop in signal intensity, and then how good your antenna is, and suddenly your FM radio just sounds like static. All right,